There's this one single idea in math that connects a pirate's treasure map, a rocket launch, and the graphics in your favorite video game. Sounds kind of crazy, right? Well, that idea is the vector. And I know it sounds complex, but it's really just about giving perfect directions. We're going to see just how powerful this one little idea can be. All right, so let's kick things off with a little puzzle. You've got a treasure map on one hand and a rocket launch on the other. What in the world do they have in common? I mean, they seem like totally different things, right? But here's the secret they both share. Just knowing a distance isn't enough. You need something more. You have to know which way to go. And that, right there, that combo of distance and direction, that's the soul of a vector. Okay, so this is really the core difference right here. Look, if I tell you, hey, go 20 miles, what's your first question going to be? 20 miles where? Exactly. That first instruction is what we call a scalar. It's got magnitude, the size, the 20 miles, but zero direction. But if I say go 20 miles northeast, well, now you've got a complete instruction. You've got the magnitude, 20 miles, and you've got the direction, northeast. And that is a vector. Okay, so we've got the basic idea down. Now let's get a little more formal and make sure we have the language right. Once we nail down the terms, we can really start to unlock how powerful this whole concept is. So first up, the scalar. The easiest way to think about this is, well, it's pretty much any measurement you can describe with just a single number. Like the temperature outside, how much your coffee costs, or the speed your car is going. These are all scalars. They're telling you how much, but they're not telling you which way. And then, of course, we have the vector. And this is where direction becomes absolutely essential. It's the classic difference between speed and velocity, right? Speed is a scalar. You're going 60 miles an hour. Cool. But velocity, that's a vector. It's 60 miles an hour due north. See the difference? One just tells you how fast. The other tells you how fast and where you're going. And that right there is the key. So to really start playing around with these ideas, we need a language for them, a way to write them down. So let's take a quick look at the special notation for vectors, because we need to be able to tell them apart from just, regular numbers. The good news is the notation is actually pretty straightforward. When you see a letter in bold, like this A, that means we're talking about the whole shebang, the full vector, its length and its direction. But when you see that same letter but with those vertical bars around it, now we're only talking about its magnitude, its length. That's it. And believe me, keeping those two things separate in your head is absolutely crucial. Okay, so with that notation in mind, what does it actually mean if we say two vectors are equal? If I like that vector A equals vector B, does that just mean they're the same length? Or is there a little more to it? Oh yeah, there's way more to it. For two vectors to be truly equal, they have to match in both ways, no exceptions. They have to have the exact same magnitude, so same length. And they have to have the exact same direction, meaning they're perfectly parallel. You need both. One without the other just doesn't cut it. All right, definitions are down, we've got the language. Now for the really fun part, actually doing some math with these things. And the best way, by far, to think about vector math is to just picture combining different parts of a journey. So let's start with adding them. Imagine this. You walk 5 blocks east, then you take a turn and walk 3 blocks north. Okay, vector addition is basically just answering the question, so where are you now compared to where you started? It's all about finding that one single direct path that would have gotten you to the same spot. And there's a really cool way to visualize this called the triangle law. All you do is you take your first vector, A, and then you take your second vector, B, and you place the tail of B right at the tip of A, like you're continuing the journey. The answer, the sum, is just the new vector you can draw from the very beginning of A to the very end of B. See? It literally completes a triangle. Okay, so what about subtraction? Well, this is where things get really, really simple, I promise. If you know how to add vectors, you already know how to subtract them. We just have to pull a little mental trick. Instead of thinking A minus B, we're going to think A plus the opposite of B. So what is the opposite of B? It's simple. It's a vector that has the exact same length as B, but it's just pointing in the complete opposite direction. You literally just take the arrow and flip it around 180 degrees. That's all a negative vector is. Okay, one last basic operation to cover. We've added, we've subtracted, but what happens if we take a vector and multiply it by a regular old number, a scalar? Like, what does it mean to have 3 times vector A? Well, this works pretty much exactly how you think it would. The direction, it doesn't change at all. The new vector, n times a, points in the exact same direction as the original a. The only thing that changes is its length gets scaled up. It's now n times as long. So 3a is just a stretched out version of a, pointing the same way.
So there we have it. We've built up our basic vector toolkit. We know what they are, we can add them, subtract them, and scale them. Now, let's actually put these new tools to work. We're going to solve a classic geometry puzzle, and you'll see how vectors make it surprisingly simple.
So here's the setup. Picture a triangle. Let's stick one of its corners right at the origin. We'll call it O. Now the vector from O to one of the other corners is A, and the vector to the last corner is B. Okay, you with me? Now what happens if we find the exact halfway point on each of those lines and connect them? Is there some kind of hidden link between this new little line and the long side of the original triangle? Well, vectors are about to tell us.
Okay, step 1. Let's figure out the vector that takes us from point A to point B. The easiest way to do this is to take a detour through the origin. So first, we travel from A back to O, and then we go from O out to B, right? The trip from A to O is just the opposite of vector A, so that's negative A. And the trip from O to B is just vector B. So we add them up, and the path AB is just B minus A. Step 2. Now we're going to do the exact same thing, but for that smaller journey from the midpoint M to the midpoint N. Since M is the halfway point, the path from M back to O is just half of minus A. And since N is the halfway point, the path from O to N is half of B. So let's add those little pieces together, and we find that the vector Mn is half B minus half A. Okay, hang on. Let's just tidy that up a bit. We can pull that 1/2 out in front of both terms, right? So that means Mn is equal to 1/2 times B minus A. Wait a second. Does that B minus A part ring a bell? It should. And there it is. That's the punchline. Remember from step 1? B minus A is the vector AB. So what our little bit of algebra just proved is that the vector Mn is exactly 1/2 of the vector AB. How cool is that? It's just so clean and elegant, and it only took a couple of steps. And this is why vectors are so powerful. That one tiny equation, Mn equals 1/2 AB, it's telling us two huge things at once. First, it tells us the line connecting the midpoints is exactly half the length of the base. And second, because one is just a multiple of the other, it tells us that the two lines are perfectly parallel. We just solved a geometry problem using simple algebra. It's amazing. So think about it. We started with just a simple idea of giving directions, and we ended up proving a fundamental rule of geometry with just a few lines of algebra. It really makes you wonder, doesn't it? If vectors can reveal the hidden secrets of a simple triangle so beautifully, what other, much more complex patterns about our world are they just waiting to help us unlock?